Growing up in California, I was often jarred awake at night by earthquakes as the house jolted and swayed on its foundation. Long after the earth had quieted, I would lie awake, still trembling in terror and exhilaration. I'm still fascinated by earthquakes, faults, and the hazards they present. I'm particularly curious about how often large earthquakes occur, and where, and why. Today, I study these questions in the San Andreas Fault System of Southern California, where stress builds up at the border between the Pacific and North American tectonic plates and is released in large earthquakes. Understanding past earthquake behavior is critical for forecasting future earthquake hazard in this densely populated region. We can get a good sense of the timing of past earthquakes using paleoseismology, which is the study of earthquake-disrupted soil layers below ground. And paleoseismologists have put together an excellent record of large earthquakes in Southern California spanning the last 1,500 years. This tells us about how often earthquakes tend to occur, but only gives limited information about the underlying drivers of this earthquake activity. In general, we do know that the more stress that's built up on a fault, the bigger its next earthquake has the potential to be. But we still have questions about how this plays out. Do faults always reach the same amount of stress before an earthquake rupture? Is a similar amount of stress released in each earthquake? And how do stresses on the eve of past large earthquakes compare to stresses in the system today? This is where my research comes in. I take past earthquake timing and extent information from my paleoseismologist colleagues and use it as inputs for computer models that simulate the mechanical interaction of faults in Southern California. I write code for these models to estimate how stress has been built up and released over the past 1,000 years. I find that at some sites, like Indio, which has gone an unusually long time since its last earthquake, stresses may have been much higher in the past than in the present day. The amount of stress released in earthquakes at this location has also varied considerably, as we can see from the differing heights of the stress graph before each earthquake. But other sites, like Wrightwood, don't show this behavior, and the uniform stress peak heights indicate that past and present day stresses there are more similar. Mechanical insights like these give context for interpreting the earthquake record, helping us understand one component of why large earthquakes happen when and where they do. And even though we can't predict exactly when the next big one will strike, this work will help us prepare for when it does. My research, along with earthquake ground shaking models and the work of seismologists and engineers, all come together into regional seismic hazard assessments. These inform building codes, disaster relief plans, and other aspects of public policy. This work will help us understand fault behavior and be ready for future earthquakes, so we can all sleep a little better at night. Thank you.